Welcome to the Daily Space for today, December 13th. My name is Dr. Pamela Gay, and I am here to put science in your brains. Today we have a whole variety of stories coming to you from, well, kind of all over the universe. For the first one, we're going to start off with a tale of planetary woe. In this case, you can take woe how you want. Either it's having a bad day or whoa, that's kind of awesome. This planet, which has been ever so elegantly named GJ3470b, is a Neptune-like world that is snuggled up right next to the red dwarf star that it's orbiting. This particular kind of star is of interest to scientists because we just don't see them in the numbers that we would expect. As we go out looking for worlds around other stars with various missions such as Kepler, we are turning up a wealth of hot Jupiters. We are turning up terrestrial worlds. But the thing that's missing is this intermediate step, these ice giants, although at close distances to their stars, they're not exactly icy. These Neptune-massed objects, they're just deficient in what we're finding. Well, this particular discovery gives us a hint of just what might be going on. In this study, Hubble watched as this Neptune-ish object orbited its world and was able to discover that it's losing mass at unprecedented rates. We've never seen this before, and this loss of what we call the exosphere, the outer atmosphere of the planet, indicates that one of the reasons we may not be seeing all of these Neptune-like planets is when they snuggle up next to their star, they just don't have the gravity a hot Jupiter has, and they can't hold on to their atmosphere. So their superheated atmosphere with particles that are ricocheting off of one another at high velocities, well, in those collisions, particles periodically get, well, accelerated to escape velocities. So the lighter weight particles in the atmospheres of these worlds just go away. And what's left behind is a much smaller atmosphere around, well, potentially a rocky core, leaving us to see not an icy Neptune-like planet, but rather a terrestrial world that is the leftover remnant of what used to be a Neptune-like world. So this leaves us to wonder just what are all the ways you can form and reform a planet? This is part of why we're constantly trying to increase our sample size. It's only by fully understanding all the different steps that a planet can go through, all the different places it can be found, and exactly where they form, that we're able to piece together theories that are complicated enough to help us understand all the crazy things we see. This is one of those things that is often surprising even to scientists. We'll think that we understand what's going on, but it turns out the universe in its reality is far more creative than we are, and it seems to be using as much of its creativity as it can to create alien worlds around other stars. At this point, we think that GJ3470b may have lost up to 35% of its total mass in just a few billion years. Over the course of all the billions and trillions of years that this little red dwarf that it's orbiting will be out there, it will lose even more of its mass. And this is where we start to think it's going to end up just being another terrestrial world. Isn't that amazing to think about? So this leaves me with questions like, what were Mercury and Venus like before? Did they have bigger atmospheres in the past? And how would we find out in our 5.5 billion year old solar system just how much things have changed? More discoveries yet to be made. Now, continuing on, we have another tale of planetary atmosphere changes. Thank you, Sifa Kant, for the follow. I'm hoping that was a wordplay on coelacanth, the ancient fish. So in another tale of planetary news, we have a supernova affecting an atmosphere. And in this case, it's our own planet's atmosphere. In new research done at Kansas University, researchers have been trying to understand why deep in the ocean we find a spike of a very particular kind of iron mineral. In this case, what we're seeing is iron 60, a kind of isotope of iron that doesn't seem to be naturally occurring on our planet Earth and is instead related to what happens when you end up with a large number of muons hitting regular iron. It changes its identity into this iron 60. Well, in trying to understand exactly how this could have happened and just what exactly might have been the consequences, researchers have turned back the clock using computer models and realized that what we might be seeing is that 2.6 million years ago, a supernova went off just 150 light years away from Earth. And the high flux of muon particles, this is an unstable, high energy particle, similar to an electron, but unstable. These particles, as they pass through our atmosphere, can give off bits of high energy radiation as they decay from muons into other particles. They can also enhance elements when they hit them. It's thought that this bombardment of muons and other high energy particles from this supernova remnant might be the reason that we see a massive extinction. Here's how it's described in the press release. A supernova 2.6 million years ago may be related to a marine megafaunal extinction at the Pliocene-Pleistocene boundary, where 30% of the genre were estimated to become extinct. The extinction was concentrated in coastal waters, where larger organisms would catch a greater radiation dose from the muons. So here what they're saying is as the muons go through the top layers of the water, they are interacting in ways that are deadly to the life that lived there. In particular, they call out the Hangoutathon shark. It is possible that the event that caused the Hangoutathon, the source of so many really terrible horror movies, the source of its extinction may have actually been an exploding star 150 light years away, 2.6 million years ago. I kind of want to see that special now. The one where like the whole sky lights up and there's a daytime star next to the sun, and yeah, sharks were killed by light. These are the things that sometimes you just have to laugh, and the fact that this particular astronomy-based press release managed to bring in Hangoutathon's extinction supernova all at once with references to the great white shark in Jaws. Kudos to this press release writer out at the University of Kansas. So those were today's top... we have one more story. Sorry. So in today's last story, we have a graph that doesn't make a whole lot of sense to look at, but I'm going to try and explain it. The blue line is the quantum fluctuations and background noise that you get in a gravitational wave detector when you simply send regular light back and forth through the detector arm. Light is made of particles that act like waves, which is one of those things that has caused a great number of people for well over a century to go, that makes no sense. But go with me on this one. Because particles act like waves, they can interfere with one another, they can build up amplitude, they can have destructive interference, and it's this interference pattern that is what the gravitational wave detectors are looking at, because they have the detectors tuned to see very carefully what the pattern is at the detector after light has traveled all the way down two different arms at right angles to one another and has been brought back to interfere. If that light changes its pattern, it means that one of those two arms changed in length, changing the distance the light had to travel, changing the way the wavelengths interfere with one another. Now, one of the assumptions that gets built into this that we wish was true was that the particles of light had this steady cadence coming out of the lasers, that they appeared one after another like lined up beads on a string of pearls. Turns out the reality is the photons aren't that well lined up, and it's more like a piece of modern art jewelry with irregular spacings between the beads. That irregular spacing can create fine level noise that blocks out our ability to see weaker gravitational lensing events. Well, scientists working with the GEO 600 gravitational wave detector have been working to find ways to alter the optics of this system. They refer to it as squeezing light, using a variety of different new optical techniques that they don't really explain anywhere in the press release or in the related websites. So I'm going to have to do more research on this. They've managed to significantly enhance their signal to noise by beating down that quantum noise. They estimate that because they've been able to do this, they're going to increase the volume of the universe that we're able to explore with gravitational wave detectors, the distance at which we're able to detect two black holes merging. They think that this volume has been increased by a factor of 7. This indicates that we'll have more events we'll be able to see and more physics we'll be able to study once they get this technique deployed on the other detectors within the LIGO-Virgo network of gravitational wave detectors. So here is to beating down the noise and squeezing light for all it's worth. Now, just as a reminder, we have a couple of cool astronomical events that are in the process of heading our way. One of those is tonight. You want to go outside tonight. Tomorrow night also works. The Gemini meteor shower is going to be emanating out of the constellation Gemini. This is how we name meteor showers. And Gemini rises in the east shortly after sunset. And as you look in its direction, you should see shooting stars radiating away, meteorites burning up in our atmosphere. It's a beautiful light show. There's a comet out if you happen to have a good pair of binoculars. Bundle up if you're someplace cold. Go outside, look up, enjoy the light show. This will be going on all throughout the night, as Gemini is going to be up all throughout the night. And the meteor shower is calculated to peak early tomorrow morning. So go out, look up, and enjoy. Now, one more advertisement of things to come in the future. December 22nd and 23rd, we here at CosmoQuest are going to be hosting a 40 hours of science for science charity stream right here on twitch.tv. Sorry, all of you who are watching this on YouTube later, you're just going to have to click on over to twitch.tv/CosmoQuestX to be able to watch this. We are going to have a variety of special guests. All of them are going to be getting listed up on our event website, Hangoutathon.org. Come see folks ranging from Phil Plait to Veronica Belmont to Phil Metzger. We're bringing in all sorts of amazing people to talk science and hopefully raise money for science. So show up, be with us, and hopefully we'll have some fun. There are a ton of giveaways. We're also going to be listing those up on the website. So stay tuned for more details. And that concludes today's episode of The Daily Space. But don't go anywhere, because I am now going to answer your questions. As always, The Daily Space is a production of the Planetary Science Institute working in collaboration with Youngstown State University. We are funded by you. those bits. Thank you so much. Looking to see who that was. Thank you so much, Ed Thompson, for the 100 bits. Can we light up the chat to celebrate? Your subscriptions sustain us, and every bit really helps. We are in the process of doing a massive fundraiser. We learned back in August that we might be experiencing budget cuts due to James Webb Space Telescope cost overruns and changes in how NASA funds citizen science. Those funding cuts came, and they were extreme. And now we're trying to figure out how to make payroll until we can find a new grant. So if you like what you see here and at CosmoQuest.org, where we invite you to help us do science, please consider giving a little. We'll make it go a long ways. So, questions, everyone, please at me in the chat. It makes it easier to find what it is you wish to ask. And I did something wrong and don't have a chat history on my screen. So if you can drop your questions back in, I'd appreciate it. So Paranor is asking, did I see the story of the neutrino picture of the sun? No, I hadn't seen that. I will try and cover that tomorrow. Thank you for that highlight. So Hanny is asking, if the muon is so unstable, how did it survive the journey to Earth? Well, it's unstable insofar as it can only last so long. High energy particles hit the upper atmosphere of our planet. They create muons. Those muons travel at near the speed of light, and then they get absorbed into the water, and that is where they choose to decay. So it's a matter of they're traveling so fast that time gets contracted for them, and they're able to last long enough in our point of view to make it all the way to the surface of the planet. Thank you, Paranor, so much. That is a new bit design. That is cool. Thank you so much. Hey, Bill Nash. So, Hanny, I don't know what all of the applications of the laser squeezing will be. My assumption would be that it's not so much that it makes better lasers as it makes more precise interference measurements. Lasers have a lot of different applications, and how you define better depends on the application. A better laser for working in your Blu-ray isn't the same thing as a better laser for in your Glowforge isn't the same as a better laser for in LIGO or Virgo. So better for what they're doing? Yes. Better for measuring gravitational waves with less quantum noise? Yes. Better in terms of able to cut things up like my Glowforge? Not so much. So for some definitions of better, yes, better lasers. Always better sharks with lasers. We need more sharks with lasers. This is just a fact. Other questions out there? So Hanny is asking, is there any timeline for the 3D Virgo to come online? Oh, for the third Virgo to come online. I'm sure there is. I don't know it. And these things always are subject to change. I have to admit, my personal philosophy has been massive instrumentation is dead to me until after it has first light. James Webb is dead to me. The schedule for LISA. Okay, see the schedule for third LIGO to come online. At least with the LISA mission, we did have the LISA Pathfinder. It was successful in terms of proof of concept. So, yeah, I don't know when the budget will allow us to launch a full-fledged LISA. For those of you who don't know what LISA is, it's a space-based gravitational wave detector that, because it will run at a very different size. It will consist of multiple spacecraft all relaying laser signals back and forth between them. Because it's a different size, located in a different place with different sources of noise, it will be able to probe different types of gravitational waves than what LIGO and Virgo here on the surface of the planet are able to detect with their different sized length arms and sensitivities. So these are two different systems. They're able to see two different regimes of gravitational waves and will help us see more of the universe using gravity instead of light. So Bill is asking, can LIGO sensors be used to detect anything else? Well, individually, we've learned that LIGO sensors are capable of detecting all sorts of really annoying things that we don't care so much about, such as when there's a local change in gravity due to rainfall or a big truck going nearby. Trying to cancel out all the noise is one of the big problems that we have. This is where we rely on multiple detectors to confirm, yes, what we just saw at this particular set of interferometric arms and what we saw at this other set can be confirmed by having timing that makes sense for the gravitational wave to have moved at the speed of light between the two different detectors. The more detectors we get, the more we're able to localize where on the sky a gravitational wave may have come from. So Hanny is asking, would Neptune's be more likely to fall into a sun than Jupiter's? It's not that they're more likely to fall into the sun that we know of. I mean, this is one of those things. Anyone who tells you they understand how planets form is full of shit. We kind of understand it, but there's a lot of details missing. So there has to be some sort of a mechanism that allows worlds to migrate inwards towards the star they're orbiting. We don't fully understand this mechanism. We do a lot of hand waving that seems to make sense in our computer models of it's friction, they get dragged through the disk, they stop because the inner part of the disk of material that planets form from has a hole in it that was blasted out by the star that the disk of material and the future planets are orbiting. But we don't really understand the details of this. And without knowing those details, I can't tell you what are the limitations on what size objects can do this. What is the frequency at which objects don't stop migrating and do make it all the way into their star? We just don't know these details yet. Now, what we're thinking is Neptunes simply get blasted apart instead of being hot Neptunes. Hot Jupiters, because they're significantly bigger than actual Jupiter most of the time, are gravitationally able to better hold on to their atmosphere. And because they can better hold on to their atmosphere, they last longer. Because they last longer, we have a higher chance of seeing them. If something only lasts for a brief moment, which cosmically might be a few million years, the probability that we're going to see it is very low. If something lasts instead for maybe a few billion years, there's a better chance that it's going to exist the same time we're looking. So that million years might mean it hasn't started to exist yet, it already ended, and it's just less likely to be seen. So if Neptunes are getting blasted apart faster, we'll see them less often. More things to figure out. We're still figuring this out. What is most amazing, though, is that we have the capacity to figure this out. We intellectually have the ability to derive the mathematics, to derive the physics, to build the computer models. We technologically can build ALMA, can build the Very Large Telescope, can build all these different instruments capable of taking the pictures that allow us to get the data to match to our models. We just don't have enough data yet. We're going to get there. We're just not there yet. So Bill is asking, is planet formation simply coincidental to the messy process of star formation? Yes. So what we do know from observations is that stars emerge out of what we poetically call cocoons and also more scientifically call proplyds, which is a more disgusting biological reference. When we look out at massive clouds of dust and gas that have extraordinarily young stars in them. So this is the pictures of the pillars of creation that were observed by Hubble that you might have seen in the past. This is the Orion Nebula that is there in the sword of Orion. As we look at all these different star forming regions, we're able to find, when we look in wavelengths of light that can penetrate through the dust, these small concentrations of material with young hot stars inside these cocoons, inside these proplyds. Over time, this collapsing bulb of gas, dust, and baby star becomes a disk that we can then see with the Atacama Large Millimeter Array, ALMA, when we look in the millimeter light. This disk of material is dynamic. It has friction. It's full of stuff that will stick together, that will, once a few things start sticking together, will gravitationally draw in more material, forming planets over time. It's basically, most of the stuff falls into the center, forms a forms a star, but some of that debris that's a little bit slower falling in, that debris forms a disk out of which the planets form. We don't know the details, but we can see the big picture parts of the process and almost slowly filling in the snapshots between frames. So Hanny is asking, did people not believe there were exoplanets or that they could never be visible? It depends on how far back you go in history. In the past century or so, there's clear science fiction references. Actually, in the past several centuries, there's science fiction references to alien life. And once we started realizing how sun-centered solar systems work, this idea that the planets go around stars and there's other stars out there, people started to imagine, well, what if? But we didn't know the probabilities. And in fact, we didn't even understand if it was common for there to be planets or uncommon for there to be planets. We found our first hint at chunks of rock orbiting dead stars with white dwarf observations that were made in 1991. Neutron star observations that were made in 1991. In the radio, they were able to measure small changes in the pulsation period of neutron stars that were indicative of the neutron star getting yanked to and fro by the gravity of planets orbiting around it. In this case, I'm talking more like chunks of debris than actual planets. But this got us thinking, what if? And in 1995, using Doppler shift techniques, again, in this case looking at bright sunlight stars nearby, the planet 51 Peg, which is still being debated if it's real or not, it was located. And since then, we've continued to find new and interesting ways to find planets astrometrically by how they move their star around in the plane of the sky, using Doppler shifts to measure how the stars get moved to and fro, in and out of the sky, and by looking for those planets to pass in front of their stars in the case of transiting planets that we observe with Kepler so often. Now we're finding that if a star has significant abundances of stuff other than hydrogen and helium, it's probably also got planets. The places that we haven't found planets yet are globular clusters and around metal poor stars. These are stars that don't have a lot of iron and other heavy elements within their composition. Yeah, it's a galaxy full of stars, full of planets. And we had to first figure out the full of stars, and then we had to figure out the how often do planets exist. And it looks like most of the time is the correct answer. So Paranor is asking, can Saturn and its ring moons be used as an analogous planetary creation system? It's the same physics dynamically, but because the gravity is much smaller, you don't have things coalescing the same way. The way we see moons shepherding the gaps in the rings, that is comparable to the gaps that we see in protoplanetary disks. But because we're dealing with much larger masses in protoplanetary disks, the small objects in those disks are able to gravitationally pull on to the other mass, are collisionally more likely to hit one another. And both through collisions and through gravitational attraction, the small bodies in protoplanetary disks can grow and grow and grow, whereas the moons in the Saturn system are more likely to simply fall apart and give up their material to the surrounding rings, or have ice geysers to give up their material to the surrounding rings. So Fenring is asking, pure hypothetical, is there a scenario in which a habitable planet could orbit a neutron star? No. Formerly habitable planet, but currently habitable, not so much. It's a matter of the supernova that had to have occurred for that neutron star to exist would have killed any life that was on that world. Now, can you move a planet there and have the planet be habitable and terraform it and all that sort of jazz? Yeah. But it's not going to naturally be habitable as a result of having lived and died. And that dying is the key word there, having lived and then died while orbiting the neutron star. So Hanny is asking, do globular clusters have metal poor stars, or is the environment too crazy for the planets to stay around their host stars? The globular clusters that we have orbiting our own Milky Way galaxy are extraordinarily old and formed at a time when our universe just hadn't yet gotten around to making heavy elements. So when you don't have heavy elements, you end up with globular clusters that don't have heavy elements. It is possible that other heavy elements out there, not heavy elements, other globular clusters out there may have formed in different circumstances than our own. We are starting to think that globular clusters might form out of material that is getting shocked during galaxy mergers. It's possible that modern day formed globular clusters could have higher metal contents, higher ratios of heavy atoms, heavy elements, and could have planets. There is the issue, though, of it is a crazy environment. Globular clusters are one of the few places where stars collide with one another, where they get close enough that they form new binary systems, form trinary systems that are stable and unstable, and they fling one another around. And it is not unreasonable to think that planets that try to evolve in this kind of a system would get flung all over the place and become runaway planets with no star to orbit. Okay, any more questions out there? So Crispy Fried Man, who still has a really disturbing username. I've watched way too many medical dramas. Crispy Fried Man is asking, can the gravitational lensing of our own sun distort our measurements of stuff outside our gravity bubble? No. We're close enough to our sun that while it slightly bends the perspective we have if we're looking pretty much straight at it of where stars appear in the sky. These kinds of changes are only visible during an eclipse because you have to look right next to the sun to see the light getting bent. Day-to-day work, it's not an issue. You'd have to get out well past Pluto before we could start using our sun as a gravitational lens to either magnify or distort background objects. Where we are, it's a star. It's cool. It's hanging out. Yes, it is bending light, but if we're looking at that light, we're getting blinded by the sun. So we tend to look in the other direction. I'm sorry for the discussion I've now started about the Crispy Fried Man's username. Thank you. You're welcome to be here, and I will stop commenting on your name. I'm very glad that you're here. Other science questions. I'm slowly starting to feel better. And thank you for the happy birthday, Nicandria. Yes, my birthday was yesterday. I got a Triceratops footstool, and I am disgustingly pleased with my Triceratops footstool. Other questions out there? Yes, I also got flowers. It is true. I will definitely post pictures on Twitter. There's already pictures up on Instagram. They just made it to Instagram faster. Okay, other science questions. I'm totally an Ophiuchus kid. You get all the points, Ed Thompson, for knowing that. So for those of you who don't know what that refers to, the sun, as it goes through the sky, actually passes through 13 constellations, not 12. And when they talk about the zodiacal signs, it is full of lies. So first of all, if you look at the dates in the newspaper for each of the zodiac signs for the fortune telling, it makes it look like they're all equally sized, but it turns out the constellations are all completely different sizes. So that's one set of lies. And there's a 13th, and they ignore it. So there is a small band of time in the month of December where the sun was actually in the constellation. Thank you so much for the host over, Nicandria. There is a small window of time in the month of December where some of us are told that we're Sagittarius or Scorpius babies, but we were actually born when the sun was in the constellation Ophiuchus, the snake handler. So I can't handle snakes. The two facts are not related in any way whatsoever. I simply grew up with a dad from Texas. So yeah. Gluten-free Space is asking, how can we detect gravitational waves with instruments like LIGO if they are ripples in space-time? Wouldn't the laser beams be distorted also? So it's because the laser beams are distorted that we're able to see this. What happens is you have waves that interfere, like a set of waves in a lake. And I wish I had an animation for this here, but I don't. And if the paths that the waves travel are one set of distances, the light interferes constructively and you end up with a bright spot on your detector. If it is a different length, they interact destructively, and this has to do with the color of light. So because we're not shifting the color of the light, we're shifting instead the path that the light is traveling. We can change how the waves interfere with one another, changing the brightness of the interference pattern on the detector. So the gravitational wave, as it moves through space, it contracts and expands space with its passage, changing the distance between the arms, and it's that change in distance for that one color of light being produced by our laser that we're able to measure. As long as the colors don't change, The frequency doesn't change. It's the distance that changes. Yes, frequency stays the same and the distance changes. Wavelength and frequency are interchangeable when you're discussing light. Okay, other science questions. I will kill this cough at some point. I'm just not there yet. Okay, if there's no more questions, I'm going to go ahead and wrap this up. And I'm going to remind all of you, if you ever miss an episode, we're on YouTube too. This episode will be appearing over on CosmoQuest's YouTube channel, and you can always download things later. Not download, you can always watch things later. So please go ahead, subscribe to us on YouTube, give us a follow on Twitch. This will let you know when new episodes are available. To those of you watching this on YouTube, thanks for being here. If you too would like to ask questions, show up at 1 p.m. Eastern. That is 11 a.m. Pacific, 6 p.m. London time at twitch.tv/CosmoQuestX. We are here most Mondays through Fridays to put science in your brain. This is produced in coordination with CosmoQuest.org, where we invite you to help us map out other worlds in our solar system. Go ahead, click on over and help us, find the scientifically interesting places and the safe places to land on other worlds. We are a production of the Planetary Science Institute, working in collaboration with Youngstown State University. We are supported by you. Every subscription really helps, and every bit really matters. Thank you so much for being here today, and hopefully I'll see you here tomorrow. Same time, same bat channel, and wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember, go outside and look up. It's the Geminids. Bye-bye.